Friday, everybody. Today we're going to do lesson 10 in Unit 8, which is an add-on, so it's not in your books. And this is about the factored form of a polynomial. So what we're going to be looking at in this lesson is that we're not always going to be looking at quadratics, that there are certain types of polynomials that have a higher power than 2 that we can look at and find zeros of. So let's read the beginning. Quadratic functions are just examples of polynomials that have a highest power of 2. We can have higher powered polynomials, such as cubics and quartics, whose highest powers are 3 and 4 respectively. The way that these functions look have connections to their zeros that are fairly obvious. The polynomial is in factored form. That's supposed to say if, that's why I couldn't read it. If the polynomial is in a factored form. Kirky. Okay, so for exercise number 1, we're going to look at this polynomial, x plus 5 times x minus 2 times x minus 6, and we're going to use the zero product law to algebraically solve for the zeros. So it's already factored for us, so all we have to do is find the zeros by setting each piece equal to 0. So instead of y, we're going to have this equal to 0, and we're going to break it up just like we did when we were in the previous lessons. So this is x plus 5 equals 0, this is x minus 2 equals 0, and x minus 6 equals 0, and we'll solve for each one. Hopefully you guys are getting to the point where you can just pretty much do this in your heads, you don't have to write it out. This is x is negative 5, adding 2, this is x is 2, and adding 6, x is 6. So we have 3 zeros in this case, right? So our zeros are x is negative 5, 2, and 6. So, what graphical features do the values in A represent for the function? That would be the zeros, which is where the line crosses the x-axis, which are technically the x-intercepts, right? And I'll put in parentheses zeros in case anyone is not sure what I mean. So we're going to look in the calculator and we're going to take a peek at what this looks like. So if it has 3 zeros, I'm trying to open my calculator the wrong way. If it has 3 zeros, then we should already know that it's going to cross the x-axis 3 different times. So we should be expecting something like that. So I'm going to plug this in exactly as I see it. X plus 5, x minus 2, and x minus 6. Okay, and I'm going to take a peek at my graph. I must have had it on some kind of window the last thing that I did this, so I'm going to zoom standard, which is 6, remember? Okay, and if that still doesn't work, I'm going to have to zoom out now. Something that I want you guys to notice is that when this type of thing happens, what you want to do is you want to look at your scale on the graph if there is one. It looks like I'm going to have to change my y min and my y max. So my y max is all the way up at 100. So let's change that to 100. Oh my gosh, I'm so sorry. It just came out of nowhere. And my y min should be negative 50. Okay, negative 50. And now let's see if we can see our graph better. Ah, there it is, right? Okay, so as you can see, the zeros that we just found, negative 5, boop, 2, boop, and 6, boop. So that's where our zeros are, negative 5, 2, and 6, and the graph goes up through the negative 5, then it comes back down through the 2, and back up again through the 6. And that's our sketch. Okay? So, if you recall, we did see a function like this before, and it ended up being a cubic function, right? So, you can also tell that this will be cubic because you have 3 x's here. So that's going to be x cubed eventually. Okay, so in exercise 1, if a cubic polynomial was written in standard form, the leading coefficient is equal to 1, although sometimes it will not be. So what we're going to do is we're going to look at that situation in the next exercise. So a cubic polynomial is shown graphed below that passes through the point -6 and 20. So -6 and 20 is over here, sorry, right here. Okay, they're just telling us that it passes through that point. What 3 linear binomial factors must this cubic have based on its zeros? So you're going to have to be able to do this just by looking at the graph. You need to be able to say, if the zeros are here, here, and here, then I can make a conclusion about what the binomials would look like. So this is -6 and -7. This one's -2, and this one's 5. So if the zeros are x equals -7, x equals -2, and x equals +5, then think backwards. When we solve for our zeros, we're always doing inverse operations, right? So this would have to be x plus 7 in order for us to solve and get x minus 7. This one would have to be x plus 2, and this one would have to be x minus 5, right? Does that make sense, I hope? You're basically going backwards. If I set each of these equal to 0, I would get these as my answers. Now, if a is the leading coefficient of this polynomial, meaning it's not 1, we're going to try to find it. We're going to write the polynomial's equation in factored form, including a. Then we're going to use the point -6, 220 to find the value of a. So what that means is if there was an a value here, it would be outside of this whole polynomial here. So it would be y equals a times this whole thing. So x plus 7, x plus 2, x minus 5, okay? So to do this, look at where your zeros are, you write the binomials, and if you need to find an a value, you put the a in front. Now we have this point, -6, 220, this is an x and this is a y. So to find the value of a, all I'm going to do is plug it in, plug it in. You know you guys missed that. All right, so instead of y, we're going to put in 220. A stays the same because that's what I'm trying to find. And all of my x's are getting replaced with -6. So this is -6 plus 7, -6 plus 2, -6 minus 5. Now, you could definitely just plug that whole thing into the calculator if you want. It's easy enough that you can do it in your head, though. Okay, this is 1. This is -4. And this is -11. Okay, so you end up with 220 is equal to 44 negative times a negative a. Because 1 times -4 times -11 is 44. And I just put the a in front. I divide both sides by 44. And I will find that a is equal to 5. And that's how you do it. So the full total polynomial would be y equals 5 times this whole binomial here that we came up with. X plus 7, x plus 2, x minus 5. Ta-da! Ooh. And that would be my answer. Okay? Okay, guys. Don't mind this, I spilled my coffee. We can have polynomials that have higher powers than 3. And actually have more zeros than 3. So in the next few exercises, we're going to look at quartic functions which have a highest power of 4. So as you can see, this is a quartic function, and if you haven't already made the connection yet that the power tells you how many zeros there are, this should hopefully solidify that for you. I've got a 0 here, 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 and here. 4, okay? So they're telling us that this one is passing through the point 5, 728. So we know that's an x and a y. We're going to use that later. We're going to figure out the equation of this just by using the zeros, okay? And we're going to figure out what the leading coefficient is going to be. So we're going to use our zeros first. This one is -8. So I have a 0 at -8. I have a 0 at -2. So sorry, guys. A 0 at 1. And a 0 at 6. So just like before, we're going to use these zeros to come up with a binomial, okay, for each one. Because once it's fully factored, that's how we would end up solving it. So this one would be x plus 8 in order to get negative 8. This one would be x plus 2 to get negative 2. This one would be x minus 1 to get it positive 1. And this would be x minus 6 to get a positive 6. Okay, so this time we have 4 instead of 3. So we're going to find the leading coefficient by doing y equals a times all of this. X plus 8, x plus 2, x minus 1, and x minus 6. And now in order to find a, just take my point and I plug in what I have. So y is 728 and x is 5. So it's going to be 5 plus 8, 5 plus 2, 5 minus 1, 5 minus 6. This ends up giving me 13 times 7 times 4 times negative 1. When you plug that in your calculator, you'll get negative 364a. Okay? And then from there, we divide both sides by this negative 364, and we'll find that a is equal to negative 2. So, to sum it up in one answer, I'm going to put the negative 2 in front of that whole hodgepodge. So my equation is y equals negative 2, and then put all of your binomials. X plus 8 times x plus 2, x minus 1 times x minus 6. Okay? Now, we're leaving it like this for now, but just to throw it out there, you absolutely could multiply these two things together and then multiply those two together. It would be a really long process, but you could do it. But for now, we just leave it like this. Okay. Now, it says to verify your answer using the window. So what we want to do is go back into our y equals, and we're going to put our equation in and make sure it looks just like that. We have to use that window though, because notice that's a really crazy window. So it's negative 2 times x plus 8, x plus 2, x minus 1, and x minus 6. Okay, before I graph, this window is going from 1500 down to negative 1000. So negative 1000, holy Hannah, and 1500. My cats have lost their minds. All right, and then we can see, sure enough, we get the same graph. We can even make sure the zeros are right. There's our negative 8, our negative 2, our 1, and our 6. Okay? Ta-da! Oh, geez. Okay, so you may have noticed that the scale on the y-axis for many of these polynomials is very large, and that's because of the larger exponents that are attached to the cubics and quartics, that they tend to grow quickly. Right, so if you have, an x squared function, you plug in 1 for x, it's 1. You plug in 5 for x, it jumps to 25. Think about when you're doing something cubed, right? If you do 1 cubed, it's still 1, but then when you do 5 cubed, it jumps all the way up to 125. Okay, so that's why the y scale is so large. So if the value of the leading coefficient is small, between 0 and 1, then they can be compressed. So we're going to look at a quartic here. This one is passing through the point 6, negative 9. So as you can see, this scale is much, much smaller. So we're going to figure out what the equation is of this one. So you might be already thinking that it's going to be between 0 and 1 because that's the point, right? So let's take a peek. We're going to find the equation. So we have 6 and negative 9. That's my x and y. And I'm going to find the equation of this. So I've got a 0 at negative 6. I've got a 0 at 1. And I've got a 0 at 3. And finally, I have a 0 at 7. Okay, and now I'm going to create my binomial using this. Okay, So I'm going to skip the step of writing it all out, and I'm going to go right to the step of setting up my equation. So I know it's going to be y equals a times. In order to get -6, this would have to be x plus 6. This would have to be x plus 1. Sorry, that's positive. X minus 1. This would have to be x minus 3 to get positive 3. And to get positive 7, this would have to be x minus 7. Okay? So we're going to solve for a by plugging in x and y. Okay, so we're plugging in -9 for y and 6 for x. I did plus again. -1, 6 minus 3, 6 minus 7. Okay, and here we go. We get -9 is equal to a times 12 times 5 times 3 times -1. When you plug this into your calculator, you're going to get that this is equal to -180. Just going to divide both sides by 180. I'm not sure why I didn't put that in the front. And that's going to be equal to, when you plug it in, you're going to get 0.05, okay, or 5/100. And that's your a value. So as you can see, when the a value is between 0 and 1, it's nice and small. It's compressed. So we can see a nice smaller version of this graph. So altogether, y is equal to 5/100 times all your binomials. So x plus 6, x minus 1, x minus 3, and x minus 7. And that's it. Okay? Now, they're taking it one step further here in this lesson just to determine the value of the y-intercept here. Because as you can see, it's falling in between any value that we're given. You could try to approximate it, right? It's somewhere between 0 and -10. How can we find this? We can use our new equation, and we know that the y-intercept is where x is equal to 0. So all we have to do is take our equation and plug in 0 everywhere there's an x, and then we're going to evaluate that and see what we get. So this will be 6 times -1 times -3 times -7. Plug this whole thing into your calculator, and you should get -6.3. That would be your y-intercept. And it makes sense, right? It looks like it's a little bit further than -5, so -6.3 should be good. And finally, to end, we're going to verify our answer by graphing the polynomial with that window. So you're going to put in your function, 0.05, parentheses, x plus 6, x minus 1, x minus 3, x minus 7. And the window this time is going from -40 to +30. So we don't need to be in the thousands here this time. What did I say? 40 to +30. And we'll take a peek. Ah, that's much better. And it looks just like the one in the picture. And there's our zeros. -6, 1, 3, 7. Ta-da! All right, and that's that, guys. So not a terribly tricky lesson, just something cool that we can do with our new skills with zeros. We can actually write the equation of something that has a way higher power if we know where the zeros are. Okay, have fun with the homework. I should see a lot of work. I know you can do a lot of this in your calculator, but I don't want to see just that on your pages. Okay, guys? Make sure you write everything out. Okay, have fun.